All right, round 3. I have 2 cylinders of equal size. Okay, so 2 cylinders. One has ammonia and the other has HCFC 22, both at 85 degrees Fahrenheit. Which one is easier to hypothetically carry? Okay, so basically what this question is asking is which one weighs less. Okay, if we both have them filled up, which one is going to weigh less? Now what it doesn't specify is whether we're talking about liquid or whether we are talking about vapor. So the best thing is to probably see what both weigh at 85 degrees Fahrenheit. Okay, so let's look. Okay, we don't even have to really do any math on this because we can just see whichever one is more dense is going to have a greater pounds per cubic foot. Okay, so if we have 1 cubic foot of all of these, okay, we can assume that we have 1 cubic foot of all of these because it doesn't specify. Okay, we can say it's a 1 cubic foot cylinder. All right, and we are operating at 85. So let's see. Let's do ammonia first. We're going to do liquid and vapor. Just look real quick. And then for HCFC 22, we're going to do liquid and vapor as well and see what the densities are at 85. So 85, the density of liquid is 37.25. Okay. Pounds per cubic foot. And the density of vapor is 0.5541. 5541 pounds per cubic foot. All right. Now for HCFC 22 at 85, the density of liquid is 73.42. 73.42 pounds per cubic foot. And the density of vapor is 3.1151. 3.1151 pounds per cubic foot. Now, we're trying to see which one is less dense. Okay? Which one that if we had a cubic foot of each of them, okay, we had a cylinder that was a cubic foot of one and a cylinder that was a cubic foot of the other, okay, which one would weigh less? Okay? So, if we look at these, it looks like ammonia liquid at 37.25 is less dense than HCFC 22 liquid. And vapor at 0.5541 is less than 3.1151. Okay? So both liquid and vapor ammonia at 85 degrees Fahrenheit are going to be less dense, way less than their counterparts of HCFC 22. So our answer is going to be ammonia. Let's check it out. There you go. So at 85 degrees Fahrenheit, ammonia is less dense than HCFC 22. All right, here's another example. We have 40 foot of 2-inch diameter pipe. This symbol right here means diameter. You can kind of remember it because it basically spans the diameter of the circle, right? And we are seeing how many pounds of saturated ammonia vapor at negative 20 degrees Fahrenheit are in this section of pipe. Okay, so we have 40 foot, 2 inches of pipe. How many pounds of saturated ammonia vapor? So we're looking for pounds, and we are given, what can we calculate out of this information we're given up here? What else I can think about it? We can calculate cubic feet, okay? And as we did in earlier problems, we know that if we have cubic feet and we are at saturation and we have our temperature, that we can convert to pounds, okay? We can see what that number is. So let's figure out what the volume of this pipe is. First, we have to match our units, okay? So we're looking for cubic feet because we know we have the conversion factors for that on our table. And we have feet and inches, okay? But we know that 12 inches equals 1 foot. okay? So we can convert that. So 2 inches, so 1 inch equals 1/12 of a foot, right? So 2 inches is going to equal 2/12 of a foot, or 1/6 of a foot, right? All we did was multiply that out. So we have a pipe that is, we have a cylinder, right? Pipes are cylinders, okay, that is 40 foot tall, okay, or has a diameter, of 1/6 of a foot. Right? So the equation for finding the volume of a cylinder is volume equals the area times the length. Okay? So first we have to find the area of this cross section of the pipe. Right? So we know our equation for area of a circle is area equals pi r squared. Right? Let's convert this diameter to radius real quick, which kind of just cancels out this whole little thing we did here, right? So we would have be 1/12, right? The radius is 1 inch. Okay, so we would take this, solve for area. So area equals pi times 1/12 squared. Okay, so let's solve that out real quick. Let me see if I can enter this. Okay. Where's this? There we go. Nope, that's not it. Okay, we are back now that I learned how to use a calculator, right? So we are looking for 1/12. Okay, is this. We're going to square that, all right, and we are then going to multiply it by pi, which I have also lost. This calculator sucks, man. All right, anyways, times 3.14 is 0.0218. We'll call that there. 0.0218. Area equals 0.0218 square feet. Okay, and then we multiply that by 40 foot. Okay, so volume equals area times length. So that times our 40 foot, and we are going to get 0.87222222 on into infinity. So 0.872. All right, so that is the volume of our pipe, 0.872 cubic feet. All right, so now that we have our volume, okay, in cubic feet, we can figure out how much this volume of ammonia is going to weigh at -20. Okay, so 0.0827 cubic feet over 1. Oop. I got that wrong. 0.827 cubic feet over 1. Yep. And then we're going to want cubic feet on the bottom. We're going to want pounds at the top. All right, so look at our saturation table at -20. And this is for ammonia. Are we on the ammonia table? Yep. Let's see, right here is -20. All right, so we're looking for pounds per cubic feet. That's going to be our density. All right, and did it say we're saturated ammonia vapor? Okay, so not our density of liquid, our density of vapor. Bam, follow that all the way across, times 0.0679. Okay, so fill that in. 0.0679 pounds per cubic foot of ammonia. Multiply that out. Our answer is going to be 0.059. 0.059. Okay, pounds of ammonia vapor. Right? That's not a lot of ammonia vapor, and that's because ammonia vapor isn't very dense, right? Vapors are not very dense. Versus this other problem we did up here, let's see, where we calculated how much this liquid would weigh. There we go. We calculated how much this liquid would weigh, right? It was 1,400 pounds. Okay? Liquid weighs a lot more than vapor. If you've ever picked up a balloon and then picked up a bucket of water, okay, picked up an empty bucket versus a bucket that's full, you would realize this. There's our answer, 0.059 pounds. Okay, next problem. We have how many cubic feet, so that's what we're looking for, of 20 degrees Fahrenheit saturated ammonia vapor would result from vaporizing 50 pounds of saturated ammonia at 20 degrees Fahrenheit, right? So it looks like we're keeping a constant temperature right here. So we're moving from saturated ammonia vapor, we're moving from saturated ammonia liquid, okay, NH3 liquid, right? We have 50 pounds of it. It's at 20 degrees Fahrenheit, and we are changing it to NH3 vapor. Okay, we're still going to have 50 pounds of it. It's not going to disappear. It's just changing phase, right? And it's still going to be at 20 degrees Fahrenheit because this is a latent heat transfer. Okay, this is a phase change. So really, all we have to do here, and we're looking for cubic feet. So all we're trying to see is a fancy way of saying how many cubic feet, okay, does 50 pounds of ammonia vapor take up? All right, so we have 50 pounds, and this is a problem we've done, 4 times already, right? So we have pounds, we're looking for cubic feet. Okay, we're at saturation, so we can use our saturation table. That's what this problem does tell us. And we are going to, let's see, ammonia at 20 degrees. Ammonia at 20 degrees, ammonia table, bam, there we go. And it looks like we have cubic foot per pound, that is specific volume, okay? Looking for the specific volume of vapor, not liquid, cubic feet per pound, okay? And that's going to be 5.9240. So 5.924. 5.924 cubic foot per pound, and we have 50 pounds of it, so we just multiply that out. We're left with cubic feet. 50 times 5.924 is 296.2. All right, so we have 296.2 cubic feet, okay? So if we had this liquid, we have 50 pounds of it, okay? Let's forget the L in pounds, all right? And we vaporize it. We still have 50 pounds of it, and it's going to take up a space, a volume of 296.2 cubic feet. Is that correct? A little off here, but like I said, remember that I used the old charts to make this, but fairly close, right? Close enough to say that we are good.